Hi, my name is Katie and welcome to my interactive concept 7 where we make liquid magnets or ferrofluid. So a ferrofluid is essentially a liquid magnet, ferro meaning iron from the Latin derivative ferro. For this experiment I actually wasn't able to find the correct materials that I need for this, and I'll explain what I mean by that in my presentation. So ferrofluid actually became known in the 1960s when scientists at NASA were trying to figure out a way to control liquids in space. So they discovered that nanoparticles of metal could be dispersed in oil or water, basically a carrier, and then that liquid could be controlled by a magnet. These new liquids were called ferrofluids. So the nanoparticles in ferrofluids are typically about 10 nanometers in size, making them small enough to remain suspended in a liquid medium. So that's a pretty key component to ferrofluids being able to be held in specific shapes. So for this particular experiment, we used, or should be using, 50 milliliters of toner ink. So this is a magnetic ink that is used for making checks. It's pretty specific toner ink used in specific types of printing, specifically for checks. So magnetic MICR ink is another name for it, contains iron oxide. These particles have been magnetized, and as I found out, most toners used don't actually contain this iron oxide, but rather plastics. I went into a couple different stores and Googled and looked everywhere on island, but was unable to find this specific type of toner in stock anywhere. Another option would have been to use iron shavings, which again was out of stock everywhere, but I saw a couple places that had them, like Walmart and Target, for magnet game toys to create things like this and play with different things with magnets, because iron is magnetized well like that and you can do different things with it. Anyways, I wasn't able to come across it, so I'll be explaining how this works. So we use the toner ink, which has iron oxide in it that's been magnetized. Then we have a rare earth metals magnet. So this is different than really your common magnet. You can still use a common magnet, it just won't give you as strong as an effect as if you use the rare earth metals magnet. These are made of an alloy of neodymium, iron, and boron. So this is sometimes abbreviated as NiB, but it's Nd2, Fe14, and B. Then you're gonna need your carrier fluid, which in this case of this experiment, vegetable oil, is a really easy one to use that will make this liquid a ferrofluid. So what you do is you combine 2 tablespoons of vegetable oil with your 50 milliliters of toner ink in a glass container. You want to stir it up really well. Make sure that the oil mixes with the ink, and then you want to take the magnet to the glass. And when you take the magnet to the glass, it should magnetize to that magnet and create a really spiky, cool geometric shape. And it'll actually hold and suspend the liquid. So if you were to turn the glass upside down, you would see that the ferrofluid would stick to the top. It would defy gravity essentially, which is why it was so useful in space. So what's going on? How and why is this happening? Ferrofluid is a stable colloidal suspension of a superparamagnetic iron oxide nanoparticles. That just means it's a liquid that contains really, really, really tiny magnetic particles. The magnetic properties come from the magnetized iron oxide. Because they're very small, the particles turn ferromagnetic magnetite into a superparamagnetic material, meaning they don't stay magnetized when removed from a magnetic field. So they're not going to hold that charge that happens when the magnet is placed by the fluid. So that's why in the video, when the magnet was placed against the glass, the fluid created those spikes, and when the magnet was removed, it just fell down and became back into a liquid. It didn't stay magnetized, it went right back into being this magnetic fluid with magnetic properties. So These magnets normally would just run into each other and stick normally, but because of the increased surface area of the liquid, this is negated and doesn't allow the magnetite to bunch up and lose its innate properties. Once the suffocant is bonded to the nanoparticles, it's considered a ligand. The ligand also has an attraction to the carrier fluid and kind of pulls the carrier fluid with the nanoparticles as they feel the magnetic force act upon them. So we were studying ligands in this chapter that we were currently doing in this week. A ligand is an ion or molecule that binds to a central metal atom to form a coordination complex. The bonding with the metal generally involves formal donation of one or more of the ligand's electron pairs, often through Lewis bases. So ligands are usually considered Lewis bases. So when I was watching this video, my first initial thoughts were, okay, I understand that this is magnetized, but why is it creating spikes? That to me, I thought something specific was going on. And I found that ferrofluids show these spiked structures in the presence of a magnetic field. So I'm actually seeing a magnetic field visualized in a physical form, essentially. The spikes are a pattern of uplifted particles that result from placing a magnet near the ferrofluid. And this happens because these particles are so small and tiny that they are able to be suspended. And the rare earth magnet is much stronger than your traditional magnet that you might find, for a refrigerator magnet. This one's much stronger and therefore exerts a stronger field, creating that spiky appearance. And the basis for magnetism can be explained at the atomic level. Electrons have both an electrical charge and a spin. Any moving charge gives rise to a magnetic field. The spin of an electron can be oriented in one of two directions, either up or down. And when the electrons pair up in an energy, they will have opposite spins and their magnetic fields will cancel. In some atoms, there can be more electrons with spins in one direction, so you might have two going down and then another going up, than the other because they're not all paired up. This results in that there's a net magnetic field for the atom. This is a paramagnetic material, so that's what we're witnessing here. When placed in a magnetic field, the atoms in a paramagnetic material will tend to align the fields with the external one. So ferrofluids have the fluid properties of a liquid and the magnetic properties of a solid, which makes them pretty interesting substances in chemistry and physics, and also very useful in the medical field potentially. So they actually contain tiny particles of magnetic solids suspended in a liquid medium, which is why it was pretty important to have that specific type of toner ink because they actually had the iron oxide, which not all toners have that iron oxide already in it. Usually, most of them, as I was told and researched, have plastics now. So ferrofluids aren't just fun to make cool shapes with or play Etch-a-Sketch or any of those other toys or things that you can do with magnets. They also have some potentials in the medical world, I found as I was researching about ferrofluids. Superparamagnetic iron oxide nanoparticles show a potential in biomedical applications as they are small enough to be used at the cellular level. So they may be able to deliver things into the cell. I was reading about many genetic materials can be delivered into cells through DNA or RNA, and this is kind of risky. So using a ferrofluid might be a better option to deliver into the cells. They also only display magnetic behavior when in the presence of a magnetic field. So I would assume that this would be a very controlled way of practicing medicine. You would have to make sure there are no magnetic fields within the area of this treatment that's being done. So it's pretty cool that ferrofluid actually has some applications in the real world for some pretty innovative things. However, it seems like they are used less often in toner inks nowadays. So thank you for watching or hearing me explain the experiment here. And I will see you next week for our last presentation. Thank you.